In section 6.1, we are looking at rational functions and multiplying and dividing rational expressions. Recall that a rational number or fraction is a number that can be written as the quotient p over q of two integers p and q as long as q is not 0. A rational expression is an expression that can be written as the quotient p over q of two polynomials p and q as long as q is not 0. Rational expressions are sometimes used to describe functions. For example, we call the function f of x equals x squared plus 2 over x minus 3 a rational function, since x squared plus 2 over x minus 3 is a rational expression. As with fractions, a rational expression is undefined if the denominator is 0. If a variable in a rational expression is replaced with a number that makes the denominator 0, we say that the rational expression is undefined for this value of the variable. For example, the rational expression x squared plus 2 over x minus 3 is undefined when x is 3 because replacing x with 3 results in a denominator of 0. For this reason, we must exclude 3 from the domain of the function, so the domain of f is then the set of all x such that x is a real number and x is not equal to 3. In this section, we will use this set builder notation to write domains. Unless told otherwise, we assume that the domain of a function described by an equation is the set of all real numbers for which the equation is defined. So for example number 1, we're going to find the domain of each rational function. For part A, f of x equals 8x cubed plus 7x squared plus 20 all over 2. No matter what the value of x, the denominator of f of x will never be 0 because it's already 2. So that means the domain of f is the set of all x such that x is a real number. This just means I can plug anything I want into our function and it will not break the function by giving us a denominator of 0. Let's look at B. G of x equals 5x squared minus 3 over x minus 1. So to find the values that would make the denominator 0, we're just going to set the denominator equal to 0. So x minus 1 equals 0. So when I add 1 to both sides, we get that x equals 1. So when x is equal to 1, we get a denominator of 0. So that means we must exclude 1 since it's undefined at that value. So it starts off the same way, x such that x is a real number, and x is not equal to 1. Let's look at the third one. F of x equals 7x minus 2 over x squared minus 2x minus 15. So again, we need to set the denominator equal to 0 and solve. So x squared minus 2x minus 15 equals 0. And this is where the last chapter comes into play. You need to be able to factor this, set them equal to 0, and solve. So when I factor this, this becomes x minus 5 times x plus 3 equals 0. Setting each piece equal to 0, and then solve. So I'm going to add 5 to both sides. And I get x equals 5 for one of my values I cannot have. And then I'm going to subtract 3. And we get that x equals negative 3 as my other value that I cannot have. And so we have two values this time. So the set of x such that x is a real number and x is not equal to 5 and x is not equal to negative 3. So recall that a fraction is in lowest terms or simplest form if the numerator and denominator have no common factors other than 1 or negative 1. To simplify a rational expression, or to write it in lowest terms, we use a method similar to simplifying a fraction. Recall that to simplify a fraction, we essentially remove factors of 1. Our ability to do this comes from these facts. If c is not equal to 0, then c over c is just 1, and n times 1 is n. In other words, if we have a times c over b times c, we can rewrite this as a over b times c over c, but c over c is just 1, and so we end up getting just a over b. The fundamental principle of rational expression says for any rational expression p over q and any polynomial r where r is not equal to 0, we have pr over qr equals p over q times r over r, but this is just p over q times 1, and that's p over q. In general, the following steps may be used to simplify rational expressions or to write a rational expression in lowest terms. You'll completely factor the numerator and denominator of the rational expression and divide out factors common to the numerator and denominator. This is the same as removing a factor of 1. So let's look at example number 2. We have 9x squared plus 13x plus 4 all over 8x squared plus x minus 7. So we need to factor the top and the bottom. So the top would factor as 9x plus 4 and x plus 1. And the denominator is going to factor as 8x minus 7 times x plus 1. Well, what we have in common on the top and bottom is x plus 1. So we can go ahead and just get rid of those because they're just going to equal 1. And so we end up getting 9x plus 4 over 8x minus 7 as our final answer. Let's go ahead and try another one. We have 18 minus 2x squared all over x squared minus 2x minus 3. We want to go ahead and factor the top and the bottom. Well, the first thing is I can factor out a GCF of 2 on the top, and I'm left with 9 minus x squared. And the bottom can factor as x plus 1 times x minus 3. On the top we have a difference of squares, so this is going to factor as 3 plus x and 3 minus x. And the denominator is still the same. Now, if we notice, 3 minus x and x minus 3 are very similar, but they are opposites. which means we can write 3 minus x so that it looks like the denominator. I'm going to multiply it by -1, and when I do that, they're going to flip as x minus 3. And so now I can cross off the x minus 3's. And what I'm left with, we have that negative, so -2 times 3 plus x all over x plus 1. Recall that for a fraction, I can put that negative sign in 3 different places and it all means the same thing. I can keep it on the bottom, I could put it to the top, or I can put it right next to the fraction bar. So that means if I put the negative in front of the x plus 1, that's the same as putting it in front of the x plus 2, or right next to the fraction bar. Let's go ahead and look at example number 3. X cubed plus 8 over 2 plus x. So what you need to remember about the top is this is a sum of cubes. And so this factors is x plus 2 times x squared minus 2x plus 4 all over 2 plus x. But x plus 2 and 2 plus x are the exact same thing. So they are going to cancel, and we are just left with x squared minus 2x plus 4. Let's try one more. 2y squared plus 2 over y cubed minus 5y squared plus y minus 5. So on the top, we can factor out the GCF of 2. And we are left with y squared plus 1. And on the bottom, we're going to utilize factoring by grouping because we have 4 terms. And so this factors as y minus 5 over y squared plus 1. We have y squared plus 1 in common. And we end up with 2 over y minus 5. When we talk about multiplying rational expressions, this works the same way as fractions does. So if I have p over q times r over s, this just becomes pr over qs, as long as q and s are not equal to 0. To multiply rational expressions, we can completely factor the numerator and denominator, use the rule above and multiply the numerator and denominator, and then simplify by crossing out anything that looks the same or dividing the numerator and denominator by their common factors. So let's look at example number 4. Our first rational expression is as simplified as it gets. I really can't factor anything on the top and bottom. But the second one on the top, I can pull out the GCF of 2, and I'm left with n minus 2. And the bottom can be factored. And this becomes 3n plus 1 times n minus 1. And so multiplying across the top and the bottom, we have our 1 plus 3n times 2 times n minus 2. And on the bottom, we have our 2n, our 3n plus 1, and our n minus 1. Now, what do we have in common? So we have a 2 on top and a 2 on the bottom. We also have 1 plus 3n and 3n plus 1, which is the same exact thing. So the only thing I'm left with on the top is n minus 2, and on the bottom I have n times n minus 1. Let's look at the next one. X cubed minus 1 over negative 3x plus 3, and 15x squared over x squared plus x plus 1. Well, looking at the first rational expression, the top is a difference of cubes. So this factors as x minus 1 times x squared plus x plus 1. And on the bottom, we can factor out a negative 3, and we're left with x minus 1. For the next fraction or rational expression, we can't factor the top or bottom, and so we're just going to multiply across the top and bottom. We have x minus 1 times x squared plus x plus 1 times 15x squared all over. We have a negative 3, an x minus 1, and an x squared plus x plus 1 in the bottom. So what can I get rid of? We have x squared plus x plus 1 on the top and bottom. We also have an x minus 1, and we can simplify the number a little bit. We have 15 over negative 3. So 15 divided by negative 3 is going to give me negative 5. And so what I'm left over with is just negative 5x squared. Now, dividing rational expressions is just multiplication in disguise. So what we're going to use is keep, change, flip. If I have p over q divided by r over s, it's going to keep the first fraction as p over q. We change division to multiplication, and we flip the second fraction. So it becomes p over q times s over r. So it works the same way. We want to factor everything and then do keep, change, flip. So for example number 5, let's look at the first rational expression. We have 8m squared, and I can't really do anything with that. On the bottom, I can factor out a GCF of 3, and I'm left with m squared minus 4 divided by, we have our 40 over 2 minus m, which really can't be done. We can't factor this down. But look at the denominator of the first rational expression. M squared minus 4 is a difference of two squares. So what we end up getting as our factorization in the bottom is 3 times m minus 2 times m plus 2. I'm going to go ahead and change my division to multiplication, and I'm going to flip the second fraction. So now we have 2 minus m over 40. So let's go ahead and multiply these out. We multiply across the top, 8m squared times 2 minus m, and we multiply across the bottom, 3 times m minus 2 times m plus 2 times 40. Let's see what we can simplify. I could rewrite 2 minus m with my negative 1 out front, so I can cancel some stuff in the denominator. So I'm just going to write 8m squared times negative 1 times m minus 2 all over our denominator. So we can cancel m minus 2. And then what else can I cancel? Between 8 and 40, 8 goes into 40 5 times. And so we end up with negative m squared on top, all over 3 times 5, which is 15, times m plus 2. Let's go ahead and try one more. We need to factor this all out. So 18y squared plus 9y minus 2, that can be factored as 6y minus 1 times 3y plus 2. The denominator 24y squared minus 10y plus 1 can be factored as 6y minus 1 times 4y minus 1. Let's go ahead and do the cube change flip. I'm going to change this to multiplication and then flip the second fraction. So looking at the denominator, 8y squared plus 18y minus 5 can be factored as 4y minus 1 times 2y plus 5. And the denominator, which was the numerator, 3y squared plus 17y plus 10, can be factored as 3y plus 2 over y plus 5. And so I'm going to show you another way we can approach this. We can cancel on the top and bottom, but we can also cancel with cross multiplication, because once I multiply this, everything on top is still going to be on top, and everything on the bottom is still going to be on the bottom. So let's look at the first fraction. On top and bottom, we both have a 6y minus 1, so that can cancel. And with the second fraction, we don't have anything we can cancel on the top and bottom. However, with cross multiplication, I can cross off 3y plus 2 and 3y plus 2, and 4y minus 1 and 4y minus 1. So we just canceled a bunch of stuff. So on the top, I'm just left with 2y plus 5, and on the bottom, I'm left with y plus 5. Now we can't cancel the 5's and the y and just be left with 2. These pieces are connected and they cannot be separated. And so you can use cross multiplication on any of the previous problems to make your life easier, and I would highly suggest it. When dividing rational expressions, do not divide common factors out until the division is rewritten as a multiplication problem. Now, what if I have both operations inside one problem? It's going to work the same way. So let's go ahead and rewrite these by factoring. So on the top of the first rational expression, x squared minus 25, this can be factored as x plus 5, x minus 5. And this is over x plus 5 squared. So I'm just going to write x plus 5 twice. So we're able to cancel a little bit easier. In the second one, we can factor out the GCF of 3, and we're left with x plus 5 all over 4x. And remember, we're going to use keep change flip. So I'm going to change that division to multiplication, and then we flip the second fraction. So x is now on top, and we can factor the denominator as x minus 5 times x plus 2. And so let's see what we can cancel. Working in the first fraction, we have an x plus 5 on the top and bottom. Cross multiplication, I can cross out x plus 5 and x plus 5. We can even do cross multiplication if they aren't right next to each other. So this x minus 5 on top and this x minus 5 on the bottom can cancel. And we have one more. We have an x and an x. And so what I have left over on top is just a 3. And on the bottom, I have a 4 and an x plus 2.